Assalamu alaikum. My name is Muhammad Abdul. I'm from Group 1 and our topic will be about bioprinting of nerve. So let's start.
Assalamu alaikum. Nerve injuries remain a significant clinical challenge due to the limited regenerative capacity of neural tissue. While autografts are the traditional gold standard, they are often limited by donor site morbidity and tissue mismatch. 3D bioprinting has emerged as a transformative solution enabling the precise layer by layer fabrication of nerve guidance conduits NGCs that incorporate both biomaterials and living cells. This bioprinted structure mimics the complex neural microenvironment, providing the necessary structural and biological cues to guide axonal regrowth and restore functional connectivity.
Okay, now let's start to talk about the working principle of nerve bioprinting. The first principle of nerve bioprinting is the creation of biomimetic niche. We aren't just making a bridge, we are engineering a living environment. We use hybrid bioinks, mixing material like gel MA for biological support with PEGDA for mechanical strength. A key working principle here is the bilayer design, a soft interior that keeps cells alive and a tough exterior that surgeon can actually handle. To make it truly known, we often add a conductive material like graphene to help the nerve communicate electrically while they heal. How do we build this? The working principle relies on high precision hardware. For example, the RAVID system allows us to print structure with a 10 micrometer precision, matching the scale of individual cells. We also use additive lathe printing to create uniform tubular shapes. But the secret is in the architecture. We print aligned microchannels that act as a GPS for regrowing axons, and we include tiny microfibers to let blood vessels grow in, which is crucial for keeping the tissue alive over long distances. The final principle is cellular synergy. Instead of adding cells later, we embed them directly into the piping during the printing process. This results in incredibly high cells viability, over 95%. This embedded stem cell then transforms the conduit into a living factory that secretes growth factor. Data shows that these cellularized prints produce 9 times the cell growth compared to the empty scaffold. By using MRI data to customize the shape, we can print bridge that perfectly fits a patient-specific injury, potentially outperform traditional nerve grafts.
So now let's see why 3D bioprinting has potential for better neural recovery. First, it offers a critical alternative to autografts. While autografts are the current gold standard, they are limited by donor side morbidity and struggle to bridge nerve gaps which exceeds 5 millimeters. Through precision scaffolding, we can use patient MRI or CT data to fabricate anatomically accurate nerve guidance conduits or NGCs tailored to the specific geometry of an injury. Beyond just structure, bioprinting creates a biomimetic niche. This protective environment is essential for neural stem cells, which often fails in standalone therapies due to the hostile inflammatory nature of injury sites. Finally, this technology extends to advanced disease modeling. By printing neural organoids and organ-on-chip platforms, we can screen drug toxicities for neurodegenerative diseases like Alzheimer's with much higher accuracy than traditional 2D models. This effectively moves us from simple structure repair toward true functional regeneration.
Okay, so now we are going to talk about technical and economic limitations. Okay, so for the current limitation to clinical adoption, firstly, we have the vascularization challenge. Without integrating blood vessels, large scale printed suffer from nerves will suffer from central necrosis. which is the cell death. Secondly, we have the mechanical integrity, which is the difficulty in balancing soft hydrogel with the stiffness that required for surgical suturing and handling. Third one, we have the immune and biological risks. Potential for host immune activation leading to glial scarring or graft rejection instead of functional integration. The last one is the economic barriers. High fabrication costs that can reach to 15,000 per construct to, due to specialized GMP grade, cell cultivation and quality control requirements.
As for future innovations, there are three emerging technologies. First, 4D bioprinting introduces stimuli responsive scaffolds that evolve in vivo to adapt to dynamic tissue growth. Second, AI driven optimization utilizes machine learning to predict cellular behavior and refine bioink parameters for maximum precision. Finally, CRISPR enhanced cells allows to engineer neural stem cells with heightened resilience against the inflammatory environments of spinal cord injuries. These innovations help set the ground for adaptive neural regeneration.
To wrap things up, 3D bioprinting has come a long way. It started as a basic scaffolding tool, but today it can produce high resolution biometric implants that can match the performance of autografts, which are currently the gold standards, by optimizing microscale architecture and integrating neural stem cells or conductive hydrogels. These constructs are now able to bridge long gap injuries in both the peripheral and central nervous system. Of course, challenges still remain, mainly in clinical scalability and cell survival. But once these are addressed, 3D bioprinting is set to deliver personalized, off the shelf neural implants that go beyond just structural support, moving toward true functional restoration for patients. Thank you so much for this.
So that's everything from us. Thank you for listening.